Welcome to another in this series of myths and misunderstandings about laser technology. Today we're going to deal with a very complex subject. Don't run away, because it is the most important part of your laser machine. Everybody's laser machine, no matter how much money you pay for it, whatever the style, whether it's an RF machine, whether it's a glass tube machine, whether it's a diode machine, or whether it's even a fiber machine, relies on two things. First of all, the man-made light source, the laser tube or the laser source itself. And secondly, one of these sort of things, a lens. Different wavelengths of light require different types of lenses. We're mainly going to deal in this session with the sort of lenses that we need for the CO2 10.6 micron wavelength light, because it is a rather special sort of light that requires special material for the lenses. As you get towards fiber laser and diode laser, you can use just ordinary glass lenses, which are much easier to manufacture, and you get a much wider variety. With the CO2 lenses, we only have two varieties of lens that we can play with. The flavors that we have are basically plano convex, curved on one side, flat on the other, or meniscus, which is curved on one side and internally concave curved on the other side. They're the only lenses that we've got to play with this machine. Now, everybody will tell you that the correct way to use a lens is the way that it was designed, i.e. flat side down, so that the light comes in on the curved side. Believe that if you wish. It's not true, but it's a good starting point. And that's the whole point about this series that I'm making, about myths and misunderstandings. There are general rules that sort of apply, but they don't always apply. You can use them any way you like. So what we're going to do today, we're going to take a look at both the lenses and the laser beam itself, because the laser beam has a big impact on the performance of your machine. And I don't mean the power, because the power is relatively unimportant. Relatively. More power, a little bit faster cutting, if you know how to use the power, and if your tube and your lens are well matched. What do you mean if they're well matched? Surely any laser beam, any lens will do what people tell you. The longer the focal length, the deeper you can cut. Well, there's an element of truth in that, but it's only an element of truth. Let me just show you something. Everybody knows that a lens looks like this. Light comes into the lens, parallel rays of light come into the lens from the laser source and then focus down to a focal point. And then after the focal point, they expand again, like that. In this particular machine here, I've got a lens which is only 25.4 millimeters focal distance. That's very, very short. That's one of the shortest lenses that you can buy. After the focal point, this lens does that. It expands very, very quickly. I've got 70 watts on this machine. I should not, according to general principles, be able to cut a piece of 15mm acrylic with such a short focal length lens and relatively little power. People would tell me that I need probably 120, 150 watts and a 4-inch lens to cut this stuff. It's going very, very slowly, 1mm a second. But, you know, I am trying to do the impossible here. Okay, now remember this drawing? So look, there's 25.4. Let's just do an estimate. And let's just call that 15mm. Look what's happened to the cut here. Wow. It's going to be huge at the bottom of the cut. Or is it? It's about the same width as it is at the top. The only thing that we've got is a little bit of a tag just here, but it's only a little corner tag. So let me just push that out. It is a slightly funny shape for a very good reason when you understand how laser beams cut, but I'm not going to go into that today. The essence of it is, myth number one, it doesn't matter about the focal length. Lenses do funny things. They don't do what people normally tell you to. You have to find out for yourself, and I've spent a long time exploring lenses and trying to understand how laser beams and lenses interact together. Now, I've purposely used this 15mm thick material for several reasons. First of all, we're going to use this as a test piece to see what's happening to our beam on these 3 machines that I've got here. 2 of them are exactly the same tube. Yeah, they claim to be exactly the same tube, but they're not. And the third option is the RF machine, which is only half the power of this. It's only 30 watts. This is a 70-watt tube. The laser beam itself is a fascinating thing. So how did that 25mm focal length lens manage to cut a virtually parallel cut through 15mm thick acrylic? It just doesn't make sense according to all the laws of lens theory that you've seen and you understand. Something weird is going on, and it's that something weird that captivated my imagination about 5 or 6 years ago, and I've spent a long time trying to decode just how a laser beam and a lens can perform that trick. I have a little fixture here that I've designed that has got a little screen on it, and it slides backwards and forwards, and there's some markings on the side here which represent the focal distances of lenses. So if I pop my lens into a little holder there, I'm going to let you look through the eyepiece of that fixture, and as I move the screen backwards and forwards, you see that I'm moving the target in and out of focus, that grid. Okay, now this is a 1.5-inch lens, and it looks as though maybe there is the right sort of distance. The black line on there represents the front edge of the screen, and you can see here we've got 1-inch lens, 1.5 inch, 2-inch and 2.5-inch lens. This claims to be a 1.5-inch lens, so why isn't it spot on the middle there of 1.5 inches? It's probably about maybe 2 or 3 millimeter out of focus, but that's because we're looking at this lens with normal light. Its focal length is designed for use at 10.6 micron wavelength light, so it will always be different than what you can see with the naked eye. So don't get worried if you don't get a perfect match. It's one of these 4 lens types, so whichever band this happens to be in, that's the lens focal distance that the manufacturer claims it to be. The wavelength of light can affect the focal distance. Now, I've made a special holder for holding my lenses while I'm cleaning them and doing various other things with them. So we just pop that holder in there. It's like a little pair of tweezers. And what we've got here is an LED torch, which has got, as you can see, lots of single LEDs hiding in there. But that's equivalent to normal light. There's nothing special about this light at all. It's not laser beam. I get a lovely clear image on my projection screen. And if I move further away, I can make the image bigger. I mean, that's exactly how you'd expect a lens to work, because that's what it's normally doing. It's taking an image and it's making it bigger or compressing it down so that it can fit onto a smaller size inside a camera. Now, let me take exactly the same focal distance lens, but I've made a very small modification to it. Okay, we'll take a look at the modification in a minute, but let's take a look at the image. There we go, nice clear image. Let's make it bigger. Still a nice clear image. What's special about this lens? Because it has no effect on the image that you can see on that paper. No, it's not a reject lens. It's one that I made myself. Because there's some rather interesting properties about what happens when you pass a laser beam through the center of a lens. It doesn't act the same as you've just seen me act on this piece of paper. Normal light just ignores that hole in the middle there. You saw no difference in the quality of those 2 images when I projected it with normal light. Now, as I mentioned before, a laser beam is not normal light, it's man-made light. It's specially organised. There is no such thing as a natural laser beam. A laser beam is a scientific creation. It's a way of organising light in a special way. The light is still the same light that's been around for billions and trillions and forever years. But the way in which the light is organised is not the same. And that's the big difference. Lens manufacturers manufacture lenses to deal with light, normal light, not laser light. But you can say, no, that lens has been designed specially for a CO2 laser. Well, no, not really. It's been designed for 10.6 micron wavelength light. That's not the same as laser light. Laser light has got special properties. Yes, it's 10.6 micron wavelength light, that's one of its properties, but it's got other special properties as well. And those special properties apply to all laser beams, whether they be 10.6 micron wavelength, 1 micron wavelength, or 450 nanometer wavelength, which you guys with diode lasers will have. A laser beam is always approximately the same, and I will explain now what a laser beam is. Well, I think at this point we need a disclaimer. Look, I am a retired engineer. I've got many different engineering skills, but one thing I'm not is an optical engineer. Another thing that I'm not is a chemical engineer. Neither am I a physicist. So I'm totally ill-qualified to explain any of the things that I'm just about to explain. However, as an engineer, I have got curiosity and skepticism encoded in my DNA. I don't believe anything until I've looked at it and proved it for myself. So I have a very irreverent approach to science. And I think you'll understand that when you see the way in which I try and simplify and explain things with scant regard for detail. We only need the principles to explain how these machines work. We leave the details to the scientists. We're not trying to design anything, we're trying to understand the concepts. Let's get on to a little bit of science now. As I said, this is going to be very lightweight and humorous, so don't get concerned. So first of all, what is light? Well, it's a very difficult concept to explain, really, because light is nothing. I know it's all around us, but in essence, the smallest part of light is something called a photon. So, what's a photon? Well, a photon has no volume, it's got no weight, no mass, it's nothing. But it exists, it's a little packet of energy. That's what light is. It's billions and billions and trillions of photons that are all around us, all the time. They're flying in different directions. But a photon has got one unique characteristic. Although it's a little packet of energy, that packet of energy is vibrating at a frequency. Now, this is where we come to this strange thing called light waves. All right? The wavelength of a photon is its vibrational rate. And we'll talk about that a little bit more, just a little bit further on. So this little packet of vibration, called a photon, travels in a straight line forever and ever until it hits something. But we're going to stop at that point and we're going to change subject for a few seconds. And we're going to look at the things that make you and I. Yeah, it's not character, it's not charisma, it's not beauty, it is atoms. We're all made up of atoms. Everything in the universe, everything you touch, look around you, is made up of atoms. There are about, let's not get too picky, there are about 90 naturally occurring types of atom. They're the smallest building block of the universe. And atoms have all got their attractiveness to each other. They're different to each other and they're all attractive to each other in different ways and different strengths. Now imagine I've got a very pretty young lady on my arm here. Look at me. I'm not a babe magnet. Why is that pretty young lady there? She's looked into my bank account and she's decided that I'm a very rich man. So therefore, she becomes attracted to me because of my riches. how strong is that bond between us? That bond is only as strong as my bank account balance. If there's a guy over the road with a big mansion, 2 Ferraris, a yacht, and an even bigger bank balance, this penniless pretty young filly is going to be attracted to him more than me. So this bond can be broken because of a stronger bond availability over there. Something is more attractive. The fact that atoms can bond together with different strengths between every atom, but they bond together in a little clump called a molecule. And put all those molecules together and you get different materials. So that's my very crude and humorous take on chemistry, the way in which it works. Now that becomes important later on. Now the other thing about materials is another weird characteristic. I'm going to start this machine up and I'm going to show you something else. In the furtherance of science, I'm going to persuade my coffee cup to help me now. I'm going to fire the laser beam across this gap here. Now we've got no lens involved in this. This is just the laser beam bouncing off that mirror and going down into my coffee. And there we go. I'm boiling the surface of my coffee. I'm going to turn the beam on. And hey, what happened? We've managed to create a fire. Several things have happened and been demonstrated there in one go. First of all, I fired that laser beam at a piece of paper and it caught fire. So your first reaction would be, ha ha ha, the laser beam is hot. But hang on, it can't be hot because it's a beam of light, not a beam of heat. So how did that catch fire? Now we come to another interesting scientific fact. Everything, this cup, that fluid, this piece of metal, everything that you see around here is doing this. At a molecular or atomic level, it's vibrating. And it's vibrating because of the amount of energy that it's got. And the amount of energy in a molecule is a measure of its temperature. So molecules that are doing this are at room temperature. If we can make a molecule do this, it gets hotter. The faster the vibration in a molecule, the hotter it gets. So temperature is a measure of the kinetic energy content of a molecule. So if we can add more energy to a molecule, we can make it vibrate faster. And vibrating faster means it gets hotter. These are strange concepts, so we don't need to go into the detail. Just keep remembering that the amount of vibration, the more it is, the hotter it is. And that's what we did here. We sent some light waves to hit this piece of material. Or light energy are like little bullets of energy. They possess no mass, no volume, just energy. And when the energy strikes that paper, it stimulated the molecules in the paper to vibrate faster and faster and faster. And if that mechanical property, that vibration, gets violent enough, remember my bank account and that pretty young lady and how they were easily parted when my bank account dropped to zero? Well, that's what's happening to this piece of paper. The energy has got so great inside that paper that some of the molecules have decided to go somewhere else. They got broken away because of the vibration. They could not stand the stress anymore, and the physical bonds actually broke. And we created different materials because some of those pretty young ladies went to join the guy across the road and make a different material. What material did it make? Well, look, we've got some ash here. That's one of the different materials that it created. So it's changed from one chemistry to another sort of chemistry. It's a different combination of molecules. This paper burst into flames because it was shaken to destruction. It didn't actually burn. Burning is just another chemical reaction. That's where the flames came from. We were producing some exothermic reactions that were creating heat to sustain that burning action even when I took it away from the energy source. So that's another quick lesson into the chemistry of materials. Different materials will react differently to the light that hits it. We've got a piece of MDF here as opposed to a piece of paper. It produced smoke, it didn't burn, it didn't catch fire. We've had a chemical reaction in the surface there, but it's not the same chemical reaction that we had there. Okay. Different materials have got what they call different damage thresholds. This requires more energy to damage than this. Yeah, we've done some damage, but it didn't instantly burst into flames. So we've got several different concepts that we've dealt with there about the chemistry of materials and the way in which light can affect the material. The same light that made that catch fire is boiling my coffee, but it's not catching fire because it's liquid, you say. Well, yeah, think about it. We're still basically sending light energy into the surface of that material. We're heating and vibrating the molecules on the surface to such an extent that they are going above the boiling point of the liquid and they're turning into steam. There is no heat in the laser beam. It is pure energy, light energy. So now we've got 3 or 4 basic scientific principles under our belt. Let's go and look at those principles in a little bit more detail. This picture represents a typical laser source. Now, I know it looks a bit like a laser tube, a glass laser tube, but this image represents typically any mechanism that produces a laser output. Now, on the left, you'll see there's something called R equals 1. Well, that's a reflecting mirror where the reflection is 100%. And on the right-hand side, we've got a mirror which is called R less than 1. Maybe say 90%. So 90% of the image that hits it reflects back. And it is this reflecting backwards and forwards between the mirrors that creates photons. It amplifies photons. Photons? Well, we've spoken about photons, and that squiggly line on the left-hand side there is supposed to represent a photon. It's a photon with a specific wavelength. So the typical definition of a laser beam is the 3 points mentioned underneath. Number 1, it's monochrome, i.e. all the waves are exactly the same, but not necessarily in phase, as that diagram shows. They could be random. Okay? That isn't what makes a laser. The thing that makes a laser is that all those waves are synchronized and what they call coherent. Thirdly, but not necessarily, the laser beam is more or less parallel. In other words, it's collimated. That defines what a laser source is. But that's not really what we're playing with. We're not playing with a laser source. We're playing with a laser beam. And a laser beam is the thing that makes this light different to normal light. Now, what I'm going to show you here is a scientific toy. It's a scientific toy that describes a statistical occurrence that happens from randomness. So I'll just run this video. And all the beans are now, all the bearings are in the top there. Now when they're released, there's a total randomness to the way in which those, let's call them photons, happen to pass through the laser mechanism. And if we watch carefully, you'll see that every time it happens, we get a similar pattern. So from total randomness, we get order. Now here's a slow motion version of that same thing happening. You can look at the randomness that all those balls are falling down, but they still form this interesting statistical shape called a normal distribution curve, or a bell curve, or a Gaussian distribution. Depending on the way in which the mirrors inside the laser source are arranged, the distance between the mirrors, and other parameters that are unique to a laser source, we can get different output characteristics to the beam. The output characteristic you saw in that first presentation was what I would call uniform. if we want a laser beam that's a cutting laser beam, which we do for our machine, we need something called a TEM00 fundamental mode. And as you can see, it's called a Gaussian mode because there we see the shape. It's the Gaussian statistical distribution curve. Okay, now if you look at the picture above it, you'll see that the center is very dark and it fades away towards the outside. That's because that graph, the height of that graph, represents the intensity of the light, or the number of photons per unit area, if you like. The number of photons at the center of that beam is much, much higher than the number of photons at the outer edge of the beam. Now, you can tune the laser to various modes. And here we've got a first order and a much higher order mode. And you can see we get funny patterns of intensity distribution within the beam. Forget number 2 and number 3. All we're interested in is TEM00. That's ideally what we want for our laser beam. Okay, now if we take a section through the laser beam anywhere, we shall find this Gaussian distribution. Now the manufacturer of our laser tube claims that our glass tube has got a diameter, a beam of about, say, 6 millimeters. So the baseline there is 6 millimeters. Now the height of this graph at the center there represents the maximum intensity of light in the beam. Now intensity of light is a very important word, intensity. The area under this graph represents the wattage, the power of your laser tube. So let's just assume that this is 60 watts. Let's call it 60 units of area. Now this graph on the right hand side, what we've done, we've reduced the beam diameter to 2 millimeters. Now this would be typical of an RF tube, 2 millimeter beam, but we're still using 60 watts of power. But 60 watts of power, remember, over here was the area. 60 watts of power here still represents this area under the graph. But because this is a mathematically defined graph, the relationship remains the same. The intensity profile of the beam has now become very sharp, as opposed to okay, as opposed to something which may be down here, which would be blunt. So you'll hear me using these terms, sharp and blunt, when I refer to a laser beam. Right, we're out on the machine again now, and just to give you an idea where we are on the machine, we're right over on the back corner of the machine here with a block of acrylic that's as close to mirror 1 as I can sensibly get it. The problem that I have, I need 5 pairs of arms because I've got to blow on this to make sure it doesn't catch fire. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it took approximately 12 seconds to burn through there. So now we're at the front right hand corner of the machine, as far away as we can possibly get from the tube. 0, 1, 2, 3, 23, 24, 25, 26, 27, 28, 29 and more or less 30. What I'm trying to demonstrate here for you is that the more intense the light, the faster you can do damage. Look at the size of this one and look at the size of this one. Because the beam size is smaller, remember the rules about a Gaussian distribution? If the beam size is small, for the same amount of power, we shall have a sharper beam. And a sharper beam means we basically have more intensity at the center and it cuts faster. So this one cut through in 12 seconds. This one took 30 seconds. But look at the size difference in the beam. The peak intensity in this beam was much, much lower than the peak intensity in this beam. But why? These are 1 meter apart. The beam has changed only by 1 meter. Okay, so we've gone through 2 more mirrors. That's not going to make a huge difference to the amount of power. So let's run the same test on another machine which has got exactly the same specification tube in it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one is close to the tube as possible, and this one's as far away as possible. Now, when we look at these on end, there's not a huge difference. 8mm, and this one about the same, 8mm. Hardly any difference between the two of them. This is what I class as an A-grade tube. We've got 8 seconds and 12 seconds, which is reasonable difference to perform the same task. And this is 30 watts, this tube, and we're running it at full flat out again. 1, 2, 3, 4, 5, 6, 7, 8. Less than half the power, and it still made it through in 8 seconds. And here we see the problem with the RF beam. More or less straight out the tube. It's pretty damn good. We'll look at the specification for these machines in a second, but I thought I'd bring you out here and show you what's going on. Now, these are all the same sort of mirrors. Now, I can very quickly test what's going in and out of my mirror with a quick pulse test like this. We'll check what comes out of the mirror with another test, much the same. What's going in and what's coming out are more or less the same size and shape. So we do the same thing at mirror 3, and they're not a lot different either. So it must be the shape of the beam that's causing the problem after it projects quite a long way after mirror 3. I think that's supposed to be a 2mm beam, and it looks closer to 4 or 5 to me, and who knows what that is. It's a disaster. I've just added something to the laser tube. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we stop at 10 seconds. 7, 8, 9, 10. Okay, so here we've got a series of results from the 30-watt RF machine. Now, this is the beam as it exits the tube. It's claimed to be a 2mm diameter, and it's probably maybe 3mm diameter at the top there, but it did this damage in about 4 seconds. Here we're about 300mm beyond the tube, just after mirror 1, and we've already got some problems. First of all, this took about 8 seconds to get to here. This took 4 seconds. So it's already halved the amount of penetrating power. And then this is maybe a further meter on at the other extreme of the machine. So the difference between these two is immense. So then I modified the machine with something called a beam expander. The beam expander is claimed to provide a uniform beam across the whole of the bed. Well, number one, as you can see, it's seriously depressed the intensity, because after 10 seconds, as opposed to 8 seconds, we've only penetrated this much. Look at the size of the beam. Yes, it has expanded the beam, but it's also compromised the intensity at the centre of the beam. And then a further meter on, look what we've got here. It's total rubbish. It's even worse rubbish than this one. These are all generated with a 30-watt beam. What's going on? Now, if we look carefully at this beam coming out of the tube, you will see that there's a little teeny-weeny imperfection just there. It's not quite round. Now, about 300mm away, that error has grown quite substantially. And yet a meter away, look what that beam has done. Yes, we've got a central depression there, but we've got all sorts of distortion around the outside of the beam. This is the low energy outer part of the Gaussian distribution, the low intensity part. The high intensity part is there, and the lower intensity part is round here, but it's not round. Okay, so we now put the beam expander into the situation, and yes, look, we've still got this kick out the side here that we saw in the native beam. So there's obviously a small imperfection in the native beam that's coming out, which gets exaggerated as it passes through the beam expander. So then we move on a meter, and here's what the beam now looks like. We've got serious distortions. We can see that we've got little pulses of power there and a sort of central-ish power there, but look, we've got these marks around the outside here, these bubbles. Now, this is a particularly telltale piece of material, acrylic. It's a wonderful material for explaining how a laser tube works, or checking the performance of a laser tube and its power. So acrylic is a very interesting material, which is why I use it for doing this test work, because at 160 degrees C it turns to liquid, just in the same way that ice turns to water at 0 or 1 degree C. It's very similar to water in that characteristic, because when you heat this stuff up to 200 degrees C, it does exactly the same as heating water to 100 degrees C. It boils and evaporates. And what you're seeing there, very low power, which is causing the acrylic to boil, liquid boiling. You can see all these little dots around the outside, so there's little bits of power around the outside which are causing the boiling, but it's not enough to seriously evaporate it. Yes, there's a small depression there, and eventually it will make a hole. Whereas in this one, we've got such a high intensity pattern at the center of the beam, we're boiling and then evaporating away the acrylic liquid. You can see exactly the same characteristic before I put the beam expander in. You've got the boiling around the edges, you've got bubbling on the surface there, which indicates that we've got not much intensity. There is a bit of depression in the center there, where we've managed to evaporate away some of the material, but it's nothing like that one there. This is the same beam, the difference is just 1 meter difference. So what on earth is going on? Now, this is machine A, and this is machine B. Machine A and machine B have got exactly the same tube in them. They're both from Cloud Ray CR70s. This one took 12 seconds to penetrate. This one took 8 seconds to penetrate. I asked Cloud Ray to find me a tube that failed final test. And this is a B grade tube. Okay, now as you can see, it's nothing like the specification that's required for this tube. This is supposed to be a 5mm beam, and it's more like 7mm. By the time it gets a metre further on, it's about 10 or 11mm. Again, if we look on the surface, you'll see the low power boiling effect around here. Okay, now close to the tube, the intensity is high enough that it's not having a major impact. But move a metre away, and you can see how much the power, the intensity has decreased. We've got a lot of crude bubbling on the surface of the actual central cone itself, and we've got more bubbling that's occurring around the outside. Okay, so this is very definitely a B grade tube. So we compare that to my A grade tube. Virtually, you can see here, we've got a very nice clean burn with a very small amount of low intensity effect around the edge of the beam. And here we've got a much, as we move further on, we've got still the central core of the beam is doing a good job, but we've still got the outer part of the beam is causing bubbling around here, which is actually increasing, technically it's increasing the beam size, but the core of the beam is actually remaining pretty constant. Let's go and have a look at the specification for these tubes and find out what's going on. The CR70 tube from Cloud Ray is in fact an SPT tube and sold under the Cloud Ray name, but this is what SPT claim. And we've seen that my A grade tube is pretty close to this perfect laser spot that we see in the center picture here. Let's take a look at the specification for this tube. Well, they mean the beam diameter, not the spot diameter. It's between 4 and 6mm diameter. Right, we found the diameter maybe 6 or 7mm to start with. So we'll investigate that in a second. Now, there's something else that people never take any notice of, and it's something called beam divergence. Now, this is a very, very important factor, and you've seen this happening on all of the beams that I've tested. Now, beam divergence, 3.1 millirads, probably meaningless to most people, but what that really means is that the beam is not parallel. It's growing at the rate of 3.1 millimeters per meter. Now, that's very significant when it comes to the relationship between a laser beam and a lens, which we shall have to tackle in the next session. The other thing is beam quality. In this case, they call the beam quality less than or equal to 1.1. Now, what that really means is, here we see the Gaussian distribution. And we've seen this random generator, which produces a Gaussian distribution. Now, look, you can see that clearly this distribution here from the ball bearings is not a perfect match for the Gaussian distribution. That's what beam quality is. It's not a perfect match for the Gaussian distribution, but it's nearly. So if we take 1 and divide it by 1.1, we get basically 91%. In other words, the match to a pure Gaussian distribution is 91% match. That's what the manufacturer claims. So let's have a look at the 30 watt RF beam. Again, this factor here, m squared, is a definition of the beam quality. And it says it's 1.2. So it's not particularly good. But as you can see, because the beam diameter is very, very small, I get a very, very high intensity at the center. And it really doesn't matter that it's not a perfect match, because I get this incredibly high intensity, which burns through the material at an alarming rate. Remember, it only took 4 seconds to burn through 25 millimeters, whereas my CR70 tube, like 2.5 times the power, took nearly 10 seconds. But the beam divergence now is 7 millirads. That means it's growing at the rate of 7 millimeters per meter. That's horrific. So when we look at the burns from the 30 watt RF tube, we see coming straight out of the tube, we've got something in the region of about a 3 millimeter diameter beam. They promise 2 millimeters, but hey, we'll talk about that in a second. So we've gone about 300 millimeters into the beam, and we're already up to about 5 millimeters. Now, 5 plus 7 is 12 millimeters, another meter on. And look, that's the result. We've now got ourselves roughly a 12 millimeter beam. But look what's happened to the intensity. Because the beam has expanded, the peak intensity's dropped off badly, and we can't do damage as quickly. The higher the intensity, the faster the rate of damage. Look, here it is. High intensity, very fast damage, 4 seconds. So that's a problem with an RF beam expansion. It's not a problem with your machine. It's a problem with the actual laser beam shape itself and the intensity decay as the beam expands. Now, you guys with a diode laser are probably laughing your socks off, thinking, well, get yourself a diode laser. No, because a diode laser can be anything from 1.1, which matches what a glass tube can do, to 1.7. 1.7 is 44% agreement to a Gaussian distribution. So hang on, you guys with the diode laser are not going to be able to do very much good at cutting. Because if the beam is that bad, the central intensity will be very low in relation to the outer intensity of the beam, and it will be a blunt beam. Blunt beams are good for engraving. They're very, very poor for cutting. Now, the other thing that I'll point out to you about this diagram, which is very useful, is we see our Gaussian distribution here with a peak intensity, whatever it happens to be, and the diameter of the beam is in fact related to this peak intensity. So there's a standard definition for a beam diameter, which is called 1 over E squared, which in simple terms means it's 13.5% of the peak intensity value. So here we are at 13.5% of the peak intensity value, and this is the diameter that the manufacturer claims is the beam diameter. As you can see, It's not the full extent of the beam diameter, it's just a proportion, a useful proportion. Right down at this lower part of the intensity distribution, you can still do damage to material. It just takes longer and longer and longer. And as we've seen from the bubbles around the outside of my burns, this is the area here that's without very much power. If you give it long enough, it will cause bubbling and boiling, but very little evaporation. So that explains why the beam diameter is not what I find physically. The manufacturer tells you one beam diameter, but in reality, give it a long enough exposure time, and we're seeing much more of this low intensity taking place when I do a 10 or 15 or 20 second burn. Now that you stop laughing about this 7 millirads beam divergence and the horrendous effect that it has on the beam quality, this is where I said I made a modification, and I used something called a beam expander. Now the principle of a beam expander is very simple. You take a small beam, you make it bigger. In making it bigger, you can control the divergence into much more of a collimated beam, i.e. it's supposed to make the beam bigger but also more parallel, and that's one way that they control the beam divergence on an RF laser. The problem is, remember, there are two types of light. There's normal light and there is laser light. But laser light is not what we're using. We're using a laser beam. Laser light can be uniform, but a laser beam is always Gaussian, or attempting to be Gaussian in its intensity distribution, which means the intensity at the center of the beam is greater than the intensity at the edge of the beam. This is not like the spotlight that you'll see on a stage. It's not a uniform patch of light. This is a very non-uniform patch of light, which is man-made. This is the bit of light that man has modified. He's made it into something of a different shape. It's no longer uniform. It's a laser light, but it's in a special distribution. That's the bit that's man-made. Now that man-made pattern of light didn't happen till about the 1950s. But a beam expander, as you see in those two pictures, can exist in two forms. And it's based upon uniform light. Look at the title, telescope theory. Look at the titles, Figure 1 and Figure 2. One was invented by Kepler and the other was invented by Galileo. Both lived in the 1600s. They didn't know anything about laser beams in the 1600s, but were using their principles to control the straightness or parallelism of a laser beam. And I use the word beam again, not laser light. Now here's that same laser beam after I put it through a 2 times beam expander. Look, we've moved from around about a 5mm beam to maybe something like, maybe 8mm, 9mm. So it's nearly 2 to 1. In other words, we've expanded the beam by a factor of about 2. So theoretically, I should see the same picture a metre on. Do I? No. Here's our 7 or 8mm beam after it's gone through the beam expander and is 300mm away from the laser source. And here we are another metre on, and look, the beam has remained approximately the same size. So, success! The beam expander works. Yeah, but it hasn't done what we expected it to do. It's messed around with the intensity. Because look, we've got the same diameter beam-ish here, apart from this fault at the side. We've got the same diameter beam here, but we've lost all our intensity. Why is that? That's basically because, as I mentioned to you before, these guys that lived in the 1600s didn't know anything about laser beams and the central intensity, that very high intensity at the centre of the beam. These were optical devices designed for working with telescopes, normal light, images. Remember the torch picture that I showed you earlier? How my special lens, which was very, very highly damaged at the centre, had virtually no effect on the projected image that went through the lens, because it was an image of uniform light. It was not a beam of light where the maximum intensity was at the centre. We're running out of time on this session, and all we've done, we've spent time to show you that laser beams are not the simple straight line things that you see with a laser pointer. They've got all sorts of strange characteristics. We're not trying to point to things with our laser, we're trying to damage material. And to damage material, we need light energy, concentrated light energy. And if you can concentrate the light energy into a very small diameter, we can do damage very, very quickly, as you can see with this first image. We pierced through 25 millimeters of acrylic in 4 seconds. Make the diameter bigger, and the rules of Gaussian distribution say that we will not be able to damage the material as fast. And this one took 8 seconds because it's a larger diameter for the same power. So the laser beam itself has got some complex characteristics. Lenses have also got complex characteristics, and we're going to have to deal with those in the next session. We're running out of time for this session. We're going to stop here because here we've got one laser beam with all sorts of beam characteristics which damage material in different ways the further we get away from the source. Now, in the next session, we're going to talk about lenses, which equally have got as many strange characteristics as laser beams. And then we're going to mix strange characteristics of laser beams with strange characteristics of lenses, and you thought you'd got a nice simple